Hello everyone. So in this video we will try to wrap up the course summary. We will try to cover some topics which you have missed. So first, which is a very important topic and is asked a lot in the exams, is the floating point representation in IEEE format. So you can see that this is a uh, formula for getting the number, which is floating point number, which has been expressed in binary format. Uh, so it is minus 1 power s. So s is the first bit here, which is a sign bit, times 1 point f. So f is the mantissa, which is the 32 bit, which is a 23 bit long binary number. So that is what is represented by f, and e is the exponent which we get from these 8 bits. So 8 bits from the first excluding the sign bit, so that represents the e. So we get the excess of e from 127. So this is the formula. So 1 point f into 2 power e minus 127 into 1 minus 1 whole power s. So this is how a floating point number represented in 32 bit format can be interpreted. So let us see an example. So here we can see that the first sign bit is is 1, so that implies it is a negative number. So first we use minus 1 power 1, so we get a negative number. Next we find the exponent, which is 0 1 1 1 1 1 0 0. So here on expanding this into decimal format, we get e equal to 124, and as we had seen, we get e minus 127. So 2 power minus 3 comes in, and then we represent this 23 bit remaining mantissa, which represents the f part in 1 point f. So here we can see this is what it comes to, and this is the number represented after normalization. Next, another important topic is time complexity and searching and sorting. So here two basic searching procedures are there, which are linear search and binary search. So linear search is just simply, so searching is basically a process where we have to check if a number is present in an array or it is not present. So in linear search we simply check one by one whether the number is equal to the key element which we need to check with, and then break once we find it. Otherwise, if we traverse the whole array without finding it, we return it is not found. So this basically takes time complexity O of n. So O of n means at worst case we need to we need to check n times, so that is why it's O of n. Now the linear search can work on any type of array, but the binary search needs to work on a sorted array, which is either in ascending or in descending order. So the way binary search works is that we find the middle element first and compare it with the key. So if the key is suppose greater than the middle element, then we again divide the array, the two subarrays formed, we divide the upper subarray which has all the values which are more than the middle element. So in this example we have the middle element as 5. So suppose the key is equal to 3. So here we compare with 5, so we find that 3 is smaller than 5. So we further split the array from 2 3 4 5. We split this array in the middle and compare with the middle elements, which are 3 and 4. So we find that 3 is already present in there. So we compare with the n plus 1 by 2th element of the array, and we either split the left half of the array or the right half, depending on the result of the comparison. So this takes a time complexity of O of log n. Finally, the binary search time complexity. Next, we have a few sorting techniques like bubble sort, selection sort. They take a time complexity of O of n square because they run in two loops, and each going from 1 to n so it becomes O of n square. And then we have the recursive sorting technique, the merge sort and the quick sort. So these have a time complexity of O of n log n, which is better than O of n square. So we will try to cover the merge sort here. So the basic idea in merge sort is to divide the array into two halves, sort the two subarrays, and then merge the two sorted arrays subarrays into a single sorted array. So sorting the subarrays is done recursively. We are again dividing it into two subarrays, and finally the base case is that there is a single element remaining, and that is the base case of the recursion used for merging the sorting the two arrays subarrays and means merging them. So here is the program. So as we can see, this is the merge function to merge two arrays A and B into C. So we have used pointers here, and this is pretty much like the str cat function with a little bit of sorting. So as you can see, if a of I is less than b of j, we copy a of I first and increment I. Otherwise we copy b of j in the array and increment j, and we store it in the c of k location and increment k. So like this, the two arrays a and b are merged and sorted in the array C. Also the m and n are the sizes of the arrays A and B. Now this is the recursive function of merge sort. So here we have take input A and the size of A. So we declare another array B and malloc it here. Then we divide the array into two subarrays by splitting it into half. So here I equal to n by 2, and then we recursively call the merge sort function with a with the size I. So from 0 to n by 2, this applies the merge sort on that, and now the merge sort is applied on a plus I. So that becomes a plus n by 2. So that is using pointer arithmetic, we get to the middle of the array, and it has a size of n minus I. Finally we merge the array A, the array A plus I into the array B, and the sizes of A and A plus I are I and n minus I. So A and A plus I are basically pointers depicting the subarrays. So finally we complete the function, and in the end we free B. So this is another topic we would like to cover, that all pointers which are generated from malloc functions by dynamic memory allocation should ideally be freed at the end. Otherwise they will keep occupying that space and point to some random location in the memory, which are like wild pointers. So we prefer to free the pointers at the end of the program. So that's it. That's end of the course summary. Thank you.